Okay, so hi if you're on live and hi if you're watching later. If you're watching later, feel free to speed up, slow down, whatever, and you can still send me questions even if you're watching this later. I will still be happy to answer. As we're going through this tonight, I want you guys to send me as many questions as you have. 2 ways to do that. Number one, you can send them through the live stream chat box. You do have to be logged into YouTube to do that. Number two, just message me on Remind. And if you're in my class, message me through our class. If you're not in our class, you can just go right to that link that you see below me on your screen. And we're going to get started. So 4 major topics for this quest. Number 1, area between curves. Number 2, volumes with known cross sections. Number 3, volumes of revolution using the disk method. Number 4, volumes of revolution using the washer method. Those are the 4 things. On my teacher site, I have 1 video dedicated to each of those. So if you need a refresher, if you need to go back through that, that's totally fine. Those are up there. Feel free to do that. But we're going to start with area between curves and work our way through tonight. So all of this will be available later. At any point, send me questions, okay? So let's get started. I just want to take a look at this. So looking at the distance between points, right? If I looked at the distance between any 2 points, not just looking at, curves or whatever. If I look at the distance between A and B here, I'm going to think, okay, to find AB, what would I be subtracting? Would I be subtracting the X values or would I be subtracting the Y values? A and B have the same X value, correct? So the thing I would be subtracting would be the Y values on AB. Now, if I looked at one like D and F right there, notice those have the same Y values. So to get the difference between those, I would subtract the X values. So thinking about that this way and what I'm subtracting can be really helpful if you're getting stuck on, well, do I solve for X? Do I solve for Y? What do I want? If I'm looking at slicing this way, right, going this way, I'm looking at subtracting the Y values. So this should be like Y1 and Y2, and I would subtract those. So you want those solved for Y, or in terms of X, we'd say. On one like this, well, this is X2 and that's X1, so here I would be subtracting my X values. So something to keep in mind as we go through. So sometimes we need these functions in terms of X, sometimes we need them in terms of Y. And something that I would encourage you guys to do is if you're not sure, solve for X or solve for Y right off the bat. And if that's not helping you, or if you don't need it, just leave it. You don't need to come back to it. But if it helps you, then you have it, right? So if I look at one like this, maybe I want the area between these curves, I'm looking for the distance from A to B, whatever, and I'm given this, that Y equals 4 minus 1 half X squared. So let's just solve it for X, just so we get the practice with that. So I'm going to actually just swap my X and my Y so that X squared is positive. So 1 half X squared equals 4 minus Y. Subtract that from both sides. Multiply both sides by 2, so 8 minus 2y, and then square root both sides. And notice when I square root this, I get the positive or the negative square root of 8 minus 2y. So it's not just the positive square root. And that's going to be important because anytime we have a parabola, we have 2 sides. We have the positive side and the negative side. So that is it in terms of X, or in terms of Y. So this is the Y value. That's the X value. I just solved it for that given variable. So if I wanted to find this length here, what I could look at is that I know I'm cutting the x-axis. This should be dx, right? I want these in terms of x. But the real idea here is I'm subtracting my y values. These have the same x coordinate, so I'm subtracting my y values. So I'm going to subtract the y value here and the y value here. So the upper y value is my function, which is the positive square root of 8 minus 2y. Okay? And my negative, or my lower part, my b value, my y value there is 0. So that's where I'm going to start with something like this. That's where I'm going to start with something like this. Okay? So I'm just going to do one more of these, one that I want to look at just to make sure that we've got the idea with this. So let's look at one like this. We've got x values and y values, right? And I can see that one of those lines is y equals x over 2 plus a half. One of those lines is y equals 5 minus 3x. So I'm going to start off the bat, if you're not sure, by just taking these and solving for the other variable. Both of these are solved for x right now. I don't know what I'm going to use, or they're solved for y. I don't know what I'm going to use, but at least if I have it there, I know I can use it. So this top one, y equals x over 2 plus 1 half. Subtract 1 half over, divide by 2. So x is 2y minus 1. Do the same thing on the other one, solve for x. So I would get it's 5 minus y all over 3. So those are in terms of y or solved for x. So now what I can think about is, okay, the distance between those is going to be the change in the x values, because I'm subtracting those. I know it cuts the y-axis, so it should be dy. We want it in terms of y. But also think you're going to be subtracting your x coordinates, right? So I'm going to do the right-hand coordinate, which is the 5 minus y over 3, right? E is on that line, minus the left-hand coordinate, which would be 2y minus 1. And so what I see there again is to find the distance between those points, I'm just subtracting those coordinates. So very basic, but that's sort of the foundation that all of this rests on. So we're going to go from there into finding area between two curves. Area between two curves. There's actually one more of these that I want to look at, and then we'll go into the next part. So here's the last one. I've got y equals x squared, and I want to find the distance here between p and q. And notice p and q both lie on y equals x squared, right? So if I solve this for x, I actually get, when you take a square root, remember you get plus or minus square root of y. And the thing to remember here is that there is a positive and there is a negative side of any a radical function, right? Sometimes we choose to restrict the domain, but there is a positive and a negative. This side here is my positive square root of y. This side here is my negative square root of y. So when we find the general distance between those, we're going to do right minus left. And so I'm going to do my p here minus q. So that is square root of y minus negative square root of y, which is 2 radical y. So if you ever see that, that's where that comes from, the plus or minus in there, right? Okay, so send any questions on that. We haven't actually done any calculus yet. This is just looking at finding distance between two curves, but we're going to get into some calc now. So we're going to start talking about some curvy areas here. Area between two curves. That's the next place I'm going. Again, send questions as you have them, either in the YouTube chat or in the Remind chat. Totally fine. Okay, next part. So area between curves. So I'm going to start by knowing that I want to find on this particular function the area between f and g, or on this particular graph, between my values of a and b. So think about this. The area below f is that whole yellow area. And the area below g is that whole orange area. What I'm interested in finding is the area between those. And so just like you do with any shapes, you've done this since geometry, you would take the area of the bigger and subtract out the area of that smaller to get the leftover piece. So that's what we're going to do, but we rewrite it in notation as saying the integral from a to b, because that's my lower and my upper bound, of the top function here minus the bottom function, because I'm taking the integral of the top, the integral of the bottom, and I'm doing all of that with respect to x. So that's going to be something that's important, okay? It would be the exact same setup for one like this. We're going from a to b. F is my top function right here. G is my bottom function. So the distance between those would be f minus g, and I would integrate from a to b. Okay, same thing here. F is the top, g is the bottom, so I'm doing top minus bottom. And that works the same way if you're going right to left, okay? So let's actually look at one of these. So here's when we're actually going to do some calculating. So find the area between the two curves where the y-axis and x equals 1.5. So x equals 1.5 would be right about here. The y-axis is right about here. And I always like to kind of shade in this region so I get an idea of what region I mean. So I'm using that region that didn't shade super well, but I'm going to outline it here. This is the region I'm looking at. So to find that area of that region, I'm going to do the integral, and I want my bounds. So I'm starting at x equals 0, or the y-axis, and I'm going to 1.5, my upper bound, and I'm going to figure out, okay, well, what's my upper, what's my lower, what's my top, what's my bottom. So here I see that this function is the upper function. This function is the lower function. So the distance between those is going to be top minus bottom, which in this case would be x squared plus 2 minus 1 minus 1/2 x. So doing that same thing that we did before, talking about the distance between the curves, and I'm doing the upper minus the lower. So actually integrating this, let's say we need to do this by hand. In a calculator, throw it in, you're done. But let's actually do this integration. So I would do the integral from 0 to 1.5, and I'm going to simplify whenever possible. It's just going to make my life easier. So this would just be x squared. There's no other terms with that. Remember to distribute this out, so that would be plus 1/2 x. And then I've got 2 minus 1, so that's plus 1 dx. That's what I need to integrate here. So now my integral, taking the antiderivative of each part, right, do each term on its own. The antiderivative of x squared is x cubed over 3. The antiderivative of 1/2 x is x squared, and that's going to be over 2. So there's actually going to be a 1/4 out front because it's a half times the over 2. Plus the integral of 1 is just x, and I'm evaluating that from 0 to 1.5. Now the good news here is that when I plug in 0 to that, it's just going to go away, right? But when I plug in 1.5, that's when I'm going to have a little bit more in there. So 1.5 to the third over 3 plus 1.5 squared over 4 plus 1.5. And I'm going to just be subtracting 0 for my entire second term. So if this was on the AP exam or on your test tomorrow on the non-calculator section, I would be okay with you guys leaving your answer in that form. That wouldn't bother me at all. If it was a multiple choice, you'd need to calculate, but it wouldn't bother me at all if that was how you choose to leave it on either the AP or this. But if you did simplify that down, if you're feeling a little ambitious, it would be 51 over 16. Okay, please send me questions as we're working. Blow up my remind, blow up the live chat. This is to help you. Okay, we're going to go to the next page on this if you're working along with me, and if you're doing this on your own, then we're just going to another problem. All right, so I want the area between these two curves. I would not ask you to do this one without a calculator, because look at my two curves. I have f of x is x squared. That's my lower function, right? That's this. And I have g of x equals cos x, which is this. Now, I cannot tell exactly where those intersect. So this is something you would take out your handy-dandy calculator. You would second calc intersect, right? And I would look for those. So this coordinate right here, that x coordinate is, there we go. That x coordinate is at, and I'm actually just going to make this a little smaller, negative 0.824133. This coordinate is just the positive of that because this is symmetric on either side of the origin. So we're really going to get a symmetric integral here, 8241323. Those are my x values there. So when I integrate, those are going to be the bounds that I'm using, the intersection points of those. So I'd be doing the integral from negative 0.824133 to positive 0.824133. And now I'm just going to do my upper function minus my lower function. So whenever possible, try to simplify your life. Use the actual function name instead of the values. So my upper function is g of x. My lower function is f of x. So I'm going to write those, dx. And so that would be the area between those curves. Now something you can think about here is that we said this was symmetric, right? So not only could I represent it that way, but let me make this a little smaller. I could also say, well, whatever this area is, the whole region would be that area doubled, right? So occasionally on a multiple choice, you'll see something like this. you'll see the integral from 0 to 0.824133 g of x minus f of x dx. And instead of just saying, okay, well, that's 0 to that, we could take it and double it. So either of these would be fair answers because it's symmetric around the y-axis. So you could either say go from this negative to the positive value, or you could say go from 0 to the positive value and double it. Either of those are acceptable. It's just a different way to represent it. So if you see that, don't be alarmed. This came up in the stations. Don't let that freak you out, okay? Continue to send more questions as you have them. All right, we're going to do one last one of these, and then we're going to move on to volumes, because I know that's really for people where the difficulty normally lies. So, last one of these area ones is one like this. So I want to find the shaded area between these. And again, this would be one that would be a little bit more difficult to do without a calculator. You could do it. It's a little bit harder to solve for those x values, but you could set them equal, square both sides, and you'd wind up coming up with the correct x values. But I'm going to tell you guys here that my intersections there are at radical 3 over 2, negative radical 3 over 2. That's the x value. And this one is at positive radical 3 over 2. And again, I could solve this. Let's say you wanted to. If this is something you want me to solve out, send it in the remind. But I'm just going to set up how I do it. So I would set one side equal to the other side, right? Set one equal to the other. To get rid of that radical, I would square both sides. So this would give me x squared times 1 minus x squared equals 1/4 x squared. And then you can go about solving it from there. I'm not going to go through that all right now, but if that's something you want me to do, feel free to send it in the remind. I can either do it now, or I can do it at the very end if you want to wait for that. So, finding these regions. You've got two options here. The hard part with this is that here, the line is on the top and the curve is on the bottom. And here the curve is on the top and the line is on the bottom. So you wind up actually having two regions where the top and the bottom switch out. So we would need to break this up into two integrals. So what I could do here is the integral from negative radical 3 over 2 to 0 of my upper function, which is the line, so 1/2 x, minus my lower function, which is x radical 1 minus x squared dx, plus I would need to add in the other region, which is the integral from 0 to positive radical 3 over 2 of, switch your order, so x radical 1 minus x squared minus 1/2 x dx. Now again, I see some symmetry here. I see that the area is symmetric on either side of the y-axis because we've got two odd functions. So you could also pick one of those regions and say that this is, okay, double the integral from 0 radical 3 over 2 of x radical 1 minus x squared minus 1/2 x dx. Okay, just another way to represent that, again, because of the symmetry. So, send me questions. If you're feeling good about this, feel free to be like, I'm feeling good about this, let's move on. But we're going to move into some volume stuff. So, before we go any further, this is a repeat, this is a repeat, this is a repeat. All right, let's talk about known cross-sections, values of known cross-sections. I'm going to flip out of here and go to this, and I'm going to grab this giant handy-dandy stack of foam that I have here. So, not joking when I say giant, this is part of it. All right, so here's all my foam, okay? So what I want you to think about is that with any prism, the volume of that prism is the area of the base times the height, right? So area of the rectangular base times the height of this rectangle. That's true for anything. It doesn't matter what size it is. It could be anything. And you'd have base area times the height. The thing about what we're doing now is we're looking at things where the area of the cross sections are not consistent. So on this one, every single one of these cross sections are the same size, right? They're all the same size. That's why it looks like a prism. That's why anything that you look at, if I look like this, it looks like a rectangular prism because all of my cross sections are the same, okay? If I took some weird funky shape like this, now this is not pretty, but it's a solid. The cross sections here change. So we start with these smaller ones here. We've got different sized ones here. But I could still calculate the volume of this using the same idea. The idea that the volume of any of this would be each of these areas accumulated, right? So I'm accumulating those areas over a given value. This is the big idea with any volume. Disc, washer, I don't care. That volume is the accumulation of area with respect to x, or volume is the accumulation of area with respect to y. If I accumulate all of my areas together, I will get the volume. Okay, that's the big idea. That almost just spilled a whole tower of foam. All right, so we're going to do a couple of these. So we want to look at the bounded region, first of all. We want to look at what the area of a cross-section would be. So what type of cross-section we're putting on top of it. And then we want to think about, well, which axis are we building perpendicular to? So let's start with the first one. So we're going on the region in the first quadrant, bounded by y equals 4 minus x squared, x equals 0, y equals 0. And we want to be perp to the x-axis. So the first thing I would do on something like this is I would sketch it. Sketch what that region looks like. So first quadrant, first of all. So I'm only looking here. Y equals 4 minus x squared. If this confuses you, rewrite it. Y equals negative x squared plus 4. So it should have a y-intercept of 4, and it should be a sad parabola coming down, right? X equals 0, that's the y-axis. Y equals 0, that's the x-axis. And we're going perp to the x-axis. So this is what my region looks like, right there. That's the base of this solid. Any cross-section we put on top of this, we are putting on that base. Okay? So again, let me know if you have questions as we go. The first part here is to build squares on top of this. So perpendicular to the x-axis. So here's my x-axis. I'm going to place these squares so they are perpendicular to that. And we're going to have squares that come up and come off of this shape. Remember, we're talking in 3D. So if, I'm just grabbing some foam. If this is my region, right, I'm placing these on top of the region coming out three-dimensionally. Okay? So think about how we would do this. So area of a square, I know area of a square is side squared, right? So I need to figure out, well, what's the side length? So think about this picture over here again. The side of that square would be this right here, from the top to the bottom. So side of the square is from there to there, because we're building the square out from there. So the top to the bottom, this is just what we did at the beginning of the live stream, is 4 minus x squared up here, and this is just 0, so top minus bottom there. So the side length is 4 minus x squared minus 0. And I put that in there. It's top minus bottom. If you don't put the minus 0, it's not a big deal. So my area in terms of x, then, is the side length, which is 4 minus x squared, quantity squared. Right? I'm taking my side length, and I'm substituting that in there. So to find the volume, I want to accumulate that over the given region. So volume will be the integral of the area, which is this. And now I need to know my bounds here. So I know that it starts at 0 because we're in the first quadrant, but I need to know this x-intercept. So I'm just going to find the x-intercept of that function. 4 minus x squared equals 0. 4 equals x squared, so x equals plus or minus 2. We're looking in the first quadrant, so it would be 2. So the volume of this shape, where squares are built on top of this region, would be the integral from 0 to 2 of 4 minus x squared, quantity squared, dx. All right, send more questions as you have them. Now let's do semicircles. Okay, let's do semicircles. Equilateral triangles, we're going to skip for right now. So area of a semicircle. Area of a semicircle is 1/2 pi r squared. And what we need to think about here is, okay, what is the radius? So think about your shape. I'm going to go back up to this. And think about building semicircles on top of this, right? So there's semicircles coming out of that. The length here, this length right there, is actually the diameter, right? The length there is actually the diameter. So what you have to think about is this is the diameter, not the radius. Well, how would you get the radius? Take half of it. So I'm going to think about this here. Radius equals half of my diameter, which is 4 minus x squared. And I'm going to cut that in half. Okay? So plug that in. So your area function in terms of x is pi over 2 or 1/2 pi, however you want to say it. Your radius quantity squared. So that's the formula for area. Now I want volume, right? So volume, I'm going to accumulate the area. So volume is the integral from 0 to 2 of this thing, which I'm going to be extra lazy and just copy and paste. And that's going to be dx. So this would be my final volume. Now, somebody asked on the live stream chat, is there going to be an equilateral triangle, or are we going to have to do this with triangles? I would say it's safe to assume that if you know, let's say maybe it's an equilateral or it's an isosceles triangle, isosceles right triangle, where your base and height would be the same, right? It's isosceles, so those are the same. That's a pretty safe bet. That could show up. Equilateral is one I've never seen on an AP exam. It would be a more difficult one to know because you'd need to figure out the altitude, or you'd need to know this formula. I wouldn't bet a lot of money that you would see that on your quiz or test or the AP exam, but again, anything could happen. Okay, continue to send questions. We're going to do one more of these, and then we'll go into washers and discs, because again, I know that's where most of our questions have been. So let's do this one. Region bounded by y equals 2 radical x and y equals x, and we want to go perp to the y-axis now. So first, let's draw this region. So draw the region. Y equals 2 radical x is a radical function, and there's y equals x. Y equals the 2 will make it taller, so it's going to look like that. Okay. And so now what I'm going to do is I'm going to find the intersection points of that. So let's set those equals. So 2 radical x equals x. I'm going to square both sides. So this would be 4x equals x squared. So I would get x squared minus 4x equals 0, x equals 0, and x equals 4. Okay, so my intersections of this region are at x equals 0 and x equals 4. One thing I would encourage you guys to do is figure out the actual coordinates there, because it's going to make your life easier. So that's 0, 0, and that's 4, 4. So this is the region I'm building on now. Okay, that's the region I'm building on. So let's see what kind of shapes we're building from here. And one thing I would also encourage you guys to do is label these. So this is 2 radical x, and this is y equals x. And like I said at the beginning of the live stream, sometimes if you're unsure what you're going to be using, it can help you to solve for the other variable right here. So this, if I was solving for x, this would just be x equals y. That one's not too scary. This one, I would divide both sides by 2 and then square it. So x would equal y over 2 squared. So in case we need them, right? Okay, since we are going perp to the y-axis, we are building this way. So think about what we talked about at the beginning of the live stream. We are subtracting the x values here. Since we're cutting the y-axis, this will be dy. So it's good that I solved for those earlier. So rectangles of height half the base. So let's think about this. We want to have a rectangle where if this is my base, this is half the base, right? So half that distance. So area of this rectangle would be 1/2 base squared. So what I need to come up with now is a formula for the base, right? For the base. So look over at this picture. If I'm building this way, right, the bases are the difference between the two curves. So the base is going to be this minus that, right minus left. So this one is x equals y, and this one is y over 2 squared. So this is going to be area function, and it's actually a with respect to y, is y minus y over 2 squared. So my volume then is going to be the integral of that, right? Or sorry, this is your base squared 1/2. So that's your area function. I just forgot to plug in for B. So volume would be 1/2 the base squared, which is y minus y over 2 squared, dy. Again, send questions as we're doing these. If you're looking at it and you're going, I don't get it, send me a question, okay? All right, so let's pick another one of these. Let's do squares, okay? So same thing, area of a square is side squared. So we're thinking again about building squares coming up from this. So the side length of that square is still that base, right? The difference between those. So side length of the square is the same as above. So this is going to be y minus y over 2 squared, quantity squared. That's my area with respect to y. So the volume is going to be the integral of that function, the area function, dy. And on both of these, I forgot to put my bounds, so let's do that quick. Since we're going with respect to y, we're going to go from the y value to the next y value, and so both of these would be from 0 to 4. Questions, comments, concerns, things that annoy you about this, anything? Okay. All right. So continue to send them. If you want to do another one, I have other shapes here that I skipped, but I kind of hit the big ones, rectangles, semicircles, squares. Those are kind of the major ones that you'll see. Okay. So we're going to go back to area and volume. We're going to talk about washers and discs. So again, if you're following along in that document, this is the next page. Looks like this. If you are not, we're just going to walk through some stuff. Okay, I see a call for more rectangle ones. So let's do one more rectangle, and then we'll go back to washers and discs. So let's say we have this same picture, right? And we want to build a different kind of rectangle on it. So same picture, I want to build a rectangle. Maybe these rectangles are going to be really tall. So I'm going to say that here's the property of these rectangles. We're going to build rectangles where the height is 4 times bigger than the base. So whatever my base is, my height will be 4 times that, okay? So my area of that would be base times height, which would be 4 base times base, right? 4 base squared. And then I would need to plug in what I know the base length is. So again, the base length of any rectangle or any shape you lay on here would be the difference between those, right? So my base length is y minus y over 2 squared. And that base length is being squared. So I'm just plugging that in where b is here. So that's the area function. So then volume here would be integral from 0 to 4 of my area dy. Okay? All right, so let's go back to these really quick. I'm going to answer somebody's remind really quickly. Okay, take a second and read what's on your screen while I answer this. Somebody's having issues. Okay, sorry, dead air. All right, so now we want to find volumes of revolution. The thing you need to know about a volume of revolution is that we're taking this, we're revolving it around 360 degrees. And so we're always going to wind up with cross sections that are circles. This in particular would be like a washer, right? Because when I slice it, I'm getting this washer shape as my cross section. Versus something more solid. I don't have one sitting here, but my water bottle, right? That would be like a disc because that would be more solid as you're going around. So we're either summing up an infinite number of discs or an infinite number of washers, and that would give me the volume of any given solid. So think about, this says think about the amount of paper. You stack up the paper and you get this shape. So, the idea behind calculating these volumes is, again, that we are accumulating the areas, okay? Always accumulating the areas. So, we are going to do a couple of these. And I want you to think about what direction we're cutting, all of this stuff. And as we're going, I want you to send me your questions. So, before we get too far into this, here we go. Let's start with this. If you were going to find the area of a circle, just a regular old circle, it would be pi r squared, right? If you were going to find the area of a washer, you have this outer circle, and then you have this inner circle, and you're removing the inner circle. So you're going to do pi times the outer radius squared minus pi times the inner radius squared, which is the same as pi times the difference of your radii squared. Those are your cross-sectional area formulas. So area of a circle, just pi r squared. Area of a washer, the outer minus the inner. And so because of that, these are going to be what we accumulate. So when we take the integral for a disk, we're doing the integral of pi r squared. When we take the integral for a washer, we're doing the integral of pi r squared minus pi r squared. So let's look at this first one. So this says we are going between y equals 1/2 x plus 1, y equals 0, and x equals 2. And I'm revolving that around a range of different things here. So I'm first going to say, let me just solve this for x. So I'm going to take this and I'm going to solve it for x. I'm going to subtract 1. I'm going to multiply by 2. So this would give me 2y plus minus 2. In case I need it, I have it there, okay? In case I need it, I have it. So now I'm going to look at what this region looks like. And on every single one of these, that's sort of where I'm starting, what the region looks like. So y equals 1/2 x plus 1. So that's going to have a y-intercept of 1 and a slope of 1/2. And it's bounded by y equals 0, which is the x-axis, and x equals 2, which would be that vertical line. Now notice it doesn't say the y-axis. So I'm going to keep extending this until those actually meet. And I'm going to think about where that happens. I know that this is at x equals 2. And this, if we think about where those meet, well, where would this equal 0? That would have to equal 0 when x is -2. So those are my coordinates there. It can also help us to find the y value, right? We might need to go from 0 to that value. So where do these meet? Well, when this is 2, right, when that function is 2, I wind up getting 2 there. So that's 2 on the y-axis as well. Okay, so the first thing we're going to do is we're going to take this region, this triangle, we're going to rotate it around the x-axis. So I'm going to think about this coming out of my screen, rotating around, and every other point on that curve doing the same thing, right? We'd wind up with a cone. You actually did these back in the day in geometry when you got a cone, and then you could figure out the volume from there. We're going to do this using calculus. So I'm going to think about capital R being my big radius, little r being my little radius if there is one, and then V being my volume. So this one, I see that those slices would be solid. If I sliced it, I would get discs, and I would need to slice it this way to get those discs, right? Slice it that way. So this is discs, and this is dx. I'm slicing the x-axis. So I'm going to keep that in mind. Now, my radius is going to be from here to the center, right? From there to the center at any given point. And so that's going to be from the line, which is 1/2 x plus 1, to 0, so minus 0. Now the inner radius, this is a disk, so there isn't really one. It's just 0 minus 0. There isn't an inner radius. Which makes my volume of this the integral from -2 to 2 of pi times my radius, which is 1/2 x plus 1 squared dx. So that is a disk, right? It's just pi r squared. There's no inner radius. Send questions as you have them, okay? All right, next one. Let's rotate that same region around y equals 2. So this same sort of region, I'm going to sketch it in. So it looks like this. And it goes around y equals 2, which we already figured out was right here. So thinking about the way that this is going to revolve, this would revolve up and around, right? This would revolve around. And so you'd have outwardly, this would look like a cylinder. But then on the inside, you also have these other points revolving around. So on the inside, this point would stay stationary. And then these points would revolve up here to make it look like a cylinder where a cone had been removed. So if you think about slicing this, we're still slicing it down perpendicular to the x-axis. So it still looks like this for slices. But now you have this gap in the middle, right? You have this gap in the middle where even though you can't see through to the bottom, when you slice it, your slices would be washers. So here's what we need to do. We need to figure out what these radii are. So think about your outer radius. That's from your axis of rotation down to the outermost part of your shape. That would be 2 minus 0. So your outer radius is 2, always, right? Looks like a cylinder, that never changes. Your inner radius is going from your axis of rotation to that inner part. And so that's going to be 2 minus the line there, minus that line that's there. So that's 1/2 x plus 1. That's your inner radius. Now this is a washer, so what I would be doing is the integral from -2 to 2, same as before, of my pi times my outer radius squared minus my inner radius squared. And that would be the volume of that shape. Send questions as you have them. Okay, keep sending them. We're going to do a bunch of these, so keep sending them as you have them. All right, next one. We're going to revolve that same region around the line y equals 4. So same region. I'm still looking at this. And I'm going to revolve around y equals 4. So let me draw this in, and then I'm going to answer a question about the last one. So the last one was, why did we square each of those? It's a great question. So remember that what you're doing here is the integral of pi times the outer radius squared minus pi times the inner radius squared dx. Because what you're doing is you're finding the integral of the area, right? And the area of a washer is pi times the outer radius squared minus pi times the inner radius squared. So if you have this as your cross section, this would be your outer radius, and then this would be your inner radius. So the area of the washer is pi r squared, big R, minus pi r squared, little r. So when I find the volume of that, since it's a washer, that's the cross-sectional area formula. If that doesn't answer your question, send it more or say that didn't make sense and we can stop, okay? Okay, let's do another one. Let's look at this one. Same region, still going from -2 to 2, right? That hasn't changed. Now we're going around y equals 4. We know that's 2. So y equals 4 would be up here. So now I'm revolving this around. There's going to be a big gap in this one, right? So this one, this inner part would revolve around. And then this outer part would also revolve around. So the bottom would look like a washer. The top is going to look kind of like a cylinder. And what I'm going to see here is that this gets connected because this would revolve around. And so it's going to look like a cylinder that has this like angled, basically a truncated cone cut out of the middle. It's kind of hard to visualize, but think about this shape if this opening got smaller towards one end, right? Same idea. So let's think about this. This is washers for sure. It's got a big gap in the middle, and I'm slicing it perpendicular to the x-axis. So it's still this shape, still dx. So let's think about my radii. Let's go outer radius, and then let's go inner radius. Outer radius is going to be from the axis of rotation to the outer part. That's y equals 0. That's the x-axis. So this would be 4 minus 0. The inner radius is from your axis of rotation to that curve. That's the inner part. So that would be 4 minus the curve, which is 1/2 x plus 1, not squared. Okay, so that's your inner radius. And since this is a washer, I'm thinking about the fact that this would be pi r squared minus pi r squared. That's my area formula. So it would be the integral from -2 to 2 of pi, and that pi can go out front. I'm actually going to put it out front. Outer radius squared minus inner radius squared dx. So always, always, always with washers, you're doing outer radius squared minus inner radius squared. Continue to send me questions. Okay, we're going to go for as long as we need to make sure we feel okay. All right, next one. Now we're going to go around a different region. So I'm doing the same exact, or a different line. Same region. It's still this right here, right? This is still -2. This is still +2. Somebody said, how much longer will I be live streaming? I was planning to do an hour. If we need to go over, I can probably go until like 8:30. So not more than that. But feel free to come and go as much as you need to. And it'll be available live right after. So if you can't watch it, that's fine. Okay, so that's that. And I know that this is still at 2. So now we're going around the line x equals -2. So I'm going around this line right here. So I'm going to revolve this way around the line. So this top part's going to go like that. This bottom part is going to go like that also. And that's going to make a cylinder-looking thing on the outside. And then on the inside, you would have this line revolve around to look like that. So you're going to have a cylinder with basically a cone removed. Okay, a cylinder with a cone removed. That's what that would look like. I know that's not a great picture. But look at the way that you would slice this. You'd be slicing it this way now, and there would be circles in it, right? Gaps in it. So that's a washer going with respect to y. So now what I need to think about here is that this is dy, right? So I'm going to use these in terms of y for outer radius and inner radius. And in terms of y, we said this was 2y minus 2. So let's look at this. Remember that equation is y equals 2y minus 2. I'm sorry, x equals. Okay, so let's do outer radius and inner radius. So outer radius, go from your axis of rotation to your outer part, right? So that's 2 minus negative 2, or negative 2 minus 2. So whether you get positive 4 or negative 4 here, it doesn't matter because you're going to wind up squaring it. So it doesn't matter what you do. All right, inner radius. So that's going from here to your axis of rotation, right? So that's from 2y minus 2 to negative 2. Outer to inner, right to left. So now I'm going with respect to y to get this volume. And these are washers, so I'm still thinking pi r squared minus pi r squared. So this would be pi times the integral of outer radius squared. So I'm going to make that 4 squared minus inner radius squared. And can you simplify this down? Sure. Do you need to? No. Doesn't matter if you do. dy. And now think about my bounds, my lower to my upper. That's going on the y values from 0 to 2. Okay, let's do another one. Same region, x equals 2. So I'm doing the same region. I'm going here to here. This is at x equals negative 2. This is x equals positive 2. This is at y equals 2. I am rotating that around the line x equals 2. So I'm going around this line. So look at how this would look. Now we're rotating this triangle around this line. When this rotates, that will make a circular base. And then this part here would rotate out like this. That would actually make solid discs. That would make a solid cone. So this makes a solid cone. To get those slices, you'd need to go this way, dy. Okay, so I know this is going to be dy. So now let's think outer radius, inner radius. Outer radius would be from the axis of rotation to your outer radius, to your outer line, which would be that line, which is 2y minus 2, minus the axis of rotation. The inner radius, it's a disk. There is no inner radius, right? And so then your volume would be pi, the integral. There is no inner radius, so it's just pi r squared. So pi r squared 2y minus 2 minus 2 minus 4 squared dy. And my integral is going from 0 to 2, y values. Okay, last one of these, and then we'll do one more group of examples like this, and then I'll just take whatever questions you guys have. So we're going to do same region, negative 2 to positive 2. That's up to y equals 2. And I'm going to rotate this around the line x equals 3. So think about rotating this. This would be circular, right? This would be circular. So the inside would look like a cylinder. That line would rotate around to there, right? And then this outer part would rotate around like that. So it would look almost like one of those little things you use in gym class as cones, right? It would look almost like a cone with the top chopped off that was hollow through the middle. So let's think outer radius and inner radius, right? So outer radius, you're going from your axis of rotation to your outermost function. So you're doing 3 minus 2y minus 2. Or you could write it in the other order, 2y minus 2 minus 3. It doesn't matter. Inner radius, you're going from your axis of rotation to the inner radius. So you're doing 3 minus 2, which is 1. So your inner radius is always 1. So your volume here, it's a washer, and we're slicing it with respect to y, right? Would be your outer radius squared. So 3 minus 2y minus 2 squared minus your inner radius squared dy. And we're going on dy, so this would be going from 0 to 2. Okay, other questions that I can answer on those. Continue to send those as we go, okay? Continue to send those as we go. All right, last thing we're going to do is this one, and then if you don't have any questions, we will go. So this one says, set up the volume integral for the region bounded by these. Y equals x squared, y equals 0, and x equals 2. So first of all, y equals x squared, let's solve this for x. Square root both sides, so it would be plus or minus radical y. And it says, note, we only want the part in the first quadrant. So if I only care about the part in the first quadrant, then all I need to worry about there is the part that's positive, okay? So y equals x squared is going to look like this. And then it says x equals 2 and y equals 0. So this is the region that I'm talking about. That's my region that I'm working on here. So the first thing we're rotating this around is around the x-axis. So I'm going this way around the x-axis. So let me do this in another color. This would come like that, and it would look like that. So it's going to be kind of like a curvy cone, okay, like a sorry game piece. Those are slices perpendicular to the x-axis, and they make a disc. And remember here, this is 0, this is 2, and how high up does this go? Well, that's y equals x squared at x equals 2, right? So this would be at 4. So my outer radius and my inner radius here. Let's start with the outer radius. Outer radius going from my axis of rotation to the edge. That edge is x squared. So it would be x squared minus 0. Inner radius, guess what? There is none. These are discs, so that's 0. So your volume here is pi times the integral of your outer radius squared, which is x squared, minus your inner radius squared, which is 0, dx, and we're going from 0 to 2. Send questions as you have them, okay? All right, next one. Now we're going to take that same region. So I'm going to redraw that region. It looks like this. That's 0, that's 2, that's 4, and we're revolving that around the line y equals 4. So this is y equals 4, right? Revolve that around. So this is going to look like that. This is going to look like that. So this will be sort of like a cylinder on the outside. The inside would be like that. So it's going to look like a cylinder that's like scooped out in the middle, right? Scooped out. So now let's think outer radius, inner radius. So from the axis of rotation to the outer part, that is your outer radius, which is 4, minus that, which is 0. Your inner radius, you're going from your axis of rotation to this inner part, which is the curve. So you're doing 4 minus x squared. So this is going to be pi times the integral from 0 to 2 of your outer radius squared minus your inner radius squared dx. Okay, next one. Y equals 5, same region, just rotating it around a different line. So it's this same region. This color kind of stinks, sorry. This is 0, this is 2, that's 4, right? And we're going around the line y equals 5, so that's up here. So there's definitely going to be a gap in this one. So rotating this around, we're going to get like that. Rotating the outer part around, we get that. Rotating this around, we'd get that. So this is the same kind of shape, right? We're still going to have this. And we're still going to have this. And it's scooped out, but there's a hole in the bottom. Not a great picture. Sorry. Still going this way with respect to x. So that's still doing washers with respect to the x-axis. So let's do outer radius, and then let's do inner radius. Outer radius is that and that, right? So I'm going to do this here. Your outer radius is from your axis of rotation down to that point, which would be 5 minus 0. Your inner radius would be going from your axis of rotation to the inner part, which is 5 minus x squared. So this is going to be pi times the integral from 0 to 2 of 5 squared minus 5 minus x squared squared dx. Okay, I've got 3 more problems, so please continue to send me questions as you have them. I haven't gotten any in a couple minutes, so I will go back to stuff. I will leave time at the end just open for questions, but I've got 3 questions left that we're going to do. Okay, so same region again, but we're going to go around the y-axis. So this, original region looked like that. So my y-axis was here, my x-axis was here. It looked like this. And I'm going to rotate that around the y-axis. So this is going to rotate around like this. This bottom part will rotate around like that. So we're going to get, again, a cylinder-looking thing on the outside with a scooped out sort of center. So it's a cylinder with the middle scooped out. But now, to get the washer cross sections, it's going to look like this. I'm going to have to slice it that way, right? So this is dy. So I'm already going to think about the fact here that instead of using x squared, this is going to be x equals the square root of y. Okay, that's going to be important for me here. So, outer radius, inner radius. Your outer radius is from your axis of rotation to that, which is at 2. So it's 2 minus 0. Your inner radius is from the axis of rotation to that, which is square root of y minus 0. So the volume of this is pi times the integral of the outer radius squared minus the inner radius squared. And yes, that is just y. That's fine. And now look at your bounds. You're going from this point on the y-axis to this point up here. That was from 0 to 4 because your y value there is 4. Okay, next one. I got 2 more, and then I need questions. This one we're going to go around the line x equals 2. So here's my region. That's at x equals 2, right? So 0, and then that's at 4. And we're rotating around that. So this part on the bottom is going around in a circle. This part here is actually going to be symmetric there. So I'm actually going to erase that first piece I did. So this is actually going to make discs when you slice it. So you're going to get discs that are with the y-axis, so that's dy, right? Or perpendicular to the y-axis. So then let's think about our radii. So your outer radius is from your axis of rotation to there, or we could go the other way. Let's do axis of rotation to here, which is 2 minus radical y. Your inner radius is 0. There is no inner radius, so that goes away. So it would be pi times the integral of your outer radius squared minus your inner radius squared, which is 0. So that's why with discs, these just go away. There's no other r squared. And I'm going here from 0 to 4 because that's my lower and that's my upper y value. Okay, this is the last question that I have planned. Ready? Rotate around x equals 4. So same region. That's at 2, that's at 0, that's at 4. X equals 4 is here. We're going to revolve around that. So this is going to revolve like this. This is going to revolve like this. We're going to get a cylinder in the middle, okay? And then this piece here, let me pick a different color. This curve here will revolve around to there, and you're going to get this kind of shape. So you've got this kind of curved edges with an empty cylinder in the middle. So let's think about our radii. Let's start with the outer radius. We're going to go from our axis of rotation, which was at x equals 4, to our curve, our outer part. So that would be 4 minus radical y. Again, you could do radical y minus 4. Doesn't matter. Same thing. And then your inner part would be 4 and 2. So 4 minus 2. So this is pi times the integral. I'm still going from 0 to 4 because this is dy of your outer radius squared. So 4 minus radical y squared minus your inner radius squared dy. Okay, so that's all I had planned for the live stream. This whole document is on my teacher site. It's got answers in it. I will also put this one that I did up on my teacher site. Stations are there. Station keys are there. Your quiz tomorrow is half calculator, half non-calculator. And it's a quiz, so you can retake it if you need to. So don't let that stress you out. Send me questions as you're studying throughout the night. I'll still be up. I'll be around. And I'm going to wait about 5 minutes to see if anybody has any other questions. And then I'm going to roll out and go eat some dinner. Also, I am free all of 1-2 tomorrow. So if you want to come in then, come. Okay, come then. That's totally fine. I'm also there before school. Send me questions if you have them. Four topics, right? How many questions are calculator active and how many aren't? Great question. There are 2 calculator inactive or calculator active and 4 calculator inactive. So it's 4 and 2. And we'll do the calculator active second. So you'll do the inactive first, turn that in, and then you can use your calculator and grab the other part. Other questions? Anything? All right, y'all. If nobody's got other questions, I will see you guys tomorrow. You're going to do great. Think about it. Outer radius, inner radius, dy, dx. You're going to be totally fine. Volume is the accumulation of area. And come see me with questions if you have them tomorrow. All right.